Hello, everyone. I'm speaking to you from Krakow, from Poland, and I'm Rafal, and I will tell you today about caching, especially about the architectural patterns for caching that you can use in your microservice system. But first, a few words about myself. So I'm a cloud software engineer at Hazelcast. I used to work at Google and CERN before. I'm also an author of the book Continuous Delivery with Docker and Jenkins. And from time to time, I do training and conference speaking, but my main job is a developer. A few words about Hazelcast. So Hazelcast is a distributed company. It's an open source company, and it's distributed in two manners, in two senses. First, it's distributed because we produce distributed software. And the second meaning is it's a distributed company because we almost all we work remotely. So I work from my home, and we meet from time to time. We have around 40 engineers, around 140 employees in total, and we have three products which are open source. Like the first one is the most known Hazelcast IMDG, which we called Cache on Steroids. The second one is Hazelcast Jet, which is a library for stream processing. And the third one is Hazelcast Cloud, which is Hazelcast Cloud is Hazelcast put in the cloud. So if you don't want to install this yourself, you just go to the website, click, and you can use a caching cluster. Our agenda for today is pretty simple. So we will start from a very short introduction about caching, and then we will walk through all caching patterns that you can use in your system. While I'm talking, I would like you to think about two things. So first thing is which of this pattern do you use in your software? Because most probably you use some caching, and this list is complete. So you must use one of this. You must use one of this pattern. And the second question I would like you to ask yourself is, does it make sense for my system to change to any other pattern? With this in mind, let's start from the introduction. So why caching? Why do we do caching in general? Everybody does caching, and we do it mainly for two reasons. One is the performance. We want to decrease the latency, so we don't want to repeat like long-lasting computation. We just return the cached value. But the second one is resilience, which may be a little less obvious, but it's still the case. So your service can be down, but you can still give the cached value, and sometimes it's good enough. For some services, cached value is good enough. Like you can imagine like Amazon recommendation service. What you see when you click on Amazon and it recommends you something. You may get a cached value. This recommendation service can be down, but you are still fine with the cached value. So sometimes it increases the resilience. But now, how it all look like in a microservice world? So what you see is here is a classic microservice architecture. So we have services. They can be written in a different programming languages. They use each other. They have versions. Now, the question for this presentation is, where is the right place to put your caching layer? Is it inside each of microservice or outside as a separate caching unit, or maybe in front of each service? And that we'll cover in this presentation. The first pattern is the simplest one, is embedded cache. That is the diagram for embedded caching. So it is pretty simple. It looks as follows. A request goes to our system. It goes to the load balancer. It's forwarded to one of the application services. And inside the application service, we have a cache. So application checks if the value is already in cache. If yes, return the cached value. If no, do some computation and put it into cache and return to the requester. So the idea is super simple. it's that simple that you can even think about it by implementing this logic yourself. So if you like Java, that would be the code you can write. So exactly what we described. Request goes to our system. We check if it's in the cache. If it's in the cache, return the cached value. If no, do some processing, put it into cache, and return the response. Obviously, you can do it, but better not do it yourself. Don't do it yourself, because if you use caching like from the current collections or any collections in actually any language, it's not good enough, because a collection is not a cache. It doesn't have like eviction policies, no max size limit, no statistics, no built-in cache loaders, no expiration time, or no notification mechanism. So you're better off not implementing cache yourself, but use some library. Now, what is a good library for Java? For simple caching, I would say a very good library is Guava, where you can define all these parameters that were missing in the collection while constructing the cache. Another good library is EHCache, but you will find, even if you don't use Java, it's in any language, you will find a simple caching library. We can even move this idea of caching one layer higher and not operate on the cache itself, but put the caching into application layer. If you happen to use Spring, that would be the code to cache calls. So we define a service, and with one annotation cacheable, each call to this method getBook name by ISBN, it will first check if it's in the cache. If it's in the cache, return the cached value. If it's not in the cache, only then execute find book in the slow source. But be careful, because Spring, for some reason, uses concurrent hash map by default. So we are better off starting from defining your own cache manager with a different cache library. Now let's get back to the diagram we've just seen. So embedded cache, we are already discussed it. It's fine. Now, one of the problems is that imagine that a request goes to our system, and it first goes to the application on the top. It executes some long-lasting business logic, put the value into cache, returns the value. Now, the same request goes to load balancer, but this time it's load balanced to the application at the bottom. And we need to do the computation again, because these caches are completely separate. They don't know about each other. That is one of the improvements to the embedded cache would be embedded distributed cache. So the application, it will be the same, it's still the same architectural pattern. However, this time we'll use a different caching library, and we will use Hazelcast. So now all caches in our application service replicas, they form one consistent cache cluster. So no matter to which application you send a request, they use the same cache. How to define it? If we stick to this Spring example, all we have to change from our previous example is to define a different cache manager. So we use Hazelcast as our cache manager. There's no more changes. That's all you have to define. And let me show you a quick demo on that. So in this demo, I will start two application services with embedded cache, and they will form one cache cluster. So let's look at the demo. So this is exactly what we've seen on the slide. So our cache manager, and there is really nothing more in this application. It's just starting some Spring Boot web project. And if I started this 2 times, so the same application locally on my laptop, and if we wait for a moment, we always have to wait because Java start time is as always long. But if we wait, you can see the first application created a cache cluster. This means one member, And the second one we started joined the first one, and they both formed one cache layer. If we started more application, obviously there would be more members joining to this cache. Now, we may wonder how it's possible that they automatically discover themselves and automatically form a cluster. Now, I've run it on my laptop, so that's easy. They used multicast to connect to each other for the discovery. However, like in real life, in real production life, we wondered how to make it like easy for the user. And we came with the idea that there will be discovery plugins for each environment. So if your application run on the Kubernetes, you just plug in Kubernetes plugin, and it uses Kubernetes API to find other cache members. And the same for AWS, for GCP. If you use some on-premise environment, then we recommend using Eureka. So you first start a Eureka server, and then piggyback on the Eureka server for Hazelcast discovery. We actually, if you want to find more about the discovery strategy, we write a lot of blog posts on that, how to set it up on Kubernetes or on Eureka. So I recommend reading that. So that's about embedded cache. Now, as a short summary, let's look at pros and cons of embedded cache in general. So from the good sides, the configuration was super simple. We had a very low latency data access because you cannot actually do anything better than you have the cache inside your application. As you've seen, there is no ops effort needed or ops team needed because it goes together with your application. From the downsides, the management of the cache is not flexible because it scales up, down together with the application. It's limited to the JVM-based application, or it's just limited to your language of choice. If you use embedded cache in Python, it will be limited to to Python. And the data is collocated with the application, which may not sound like a big deal. However, in fact, it is for most big companies that is a huge problem, and they say, okay, it's not secure, don't do it. This way we covered the first part, the embedded cache. Let's move to the next one, which is the next pattern, the next topology, which is client server. So client server is old as the word. It's like the database style. So this is the diagram. So you set up cache as a separate unit in your system. And then it works like this. Request goes again to load balancer. It load balances the traffic to one of the application services. And they are all connected to the same cache server. So it's kind of a database style. Now, if we compare this pattern to the embedded cache, there are two main differences. The first one is obviously this part. So we have a cache server now, which means that we need to maintain it. We need to think about security and so on. But on the other hand, we can scale it as we want. So the management is more flexible. But the second thing that is very different from the embedded cache is actually this part. So now the application uses a cache client to connect to the cache server, which may not sound like a big thing, but it is, because now there's a well-defined protocol between cache client and cache server. So you may use any programming language you want to connect to your server. And it's a very common strategy that you set up a cache server, and then different applications written in different programming languages, they use different clients, but the same protocol, and they connect to the cache server. This is such a common architecture that some caching solutions, they cover only client server architecture. Like if you look at the Redis, you cannot Redis. I think it's written in C, so you cannot really embed it in your application. And the same with Memcache. So the only deployment, the only way you can deploy it, it's actually client server. If we stick to Hazelcast, so if we would like to start a server, there's just a script, again, using the same discovery mechanism. So you just start many nodes, they automatically discover themselves, and you have the server. As simple as that. If you are like, if you're a person that likes Kubernetes, or then we provide a Helm chart to run the cache server. We also provide an operator, so you have your choice in Kubernetes. So that would be like, this is the only command you have to execute to start the whole cache cluster on Kubernetes. This is how the client would look like. Again, let's stick to the Spring. So this is the configuration. You may see this get Kubernetes config set enable true. So this two lines, this two lines means use Kubernetes plugin for discovery and automatically discover my server. So coming back to the diagram, so if we already like, we already have a separate unit, like a server part. It's already separate thing to our system. So we can even go one step further and move it not only as a separate thing to maintain in our system, but move it into the cloud. So cloud is, in terms of architecture, is still like kind of client server, but it is very specific. So you could even consider this as a separate caching pattern. It is specific because server part is actually not managed inside your company, but by a cloud provider. So you don't have to worry about all organizational stuff. So these things that we had to cover in, while maintaining our own server, now you don't have to do it. Nevertheless, in terms of architecture, it's kind of a client server. Again, if you would like to see the code of the of this Spring Bean configuration, that would be our configuration for using cloud, like Hazelcast Cloud. So you see, we specify discovery token, we specify the cluster name and the cluster password, and that's all. That's all you need to connect to your cache in the cloud. And what you see here, this is an example for Hazelcast Cloud, but actually everything now in the cloud works the same. It's based on the discovery tokens, and that's how you discover this. So no static configuration. Let me show you a second demo for this presentation, which will be how to start a cluster on Hazelcast Cloud and connect to this from your application on, I will connect it from an application on my laptop. So we, if you go to the cloud hazelcast.com website, you click on the new cluster. Then obviously you need some cluster name. Let's call it a test cluster, and then select the underlying cloud provider, because we don't provide the infrastructure, then some other parameters, and create cluster. From other parameters, you can obviously set up some persistence, some encryption, and so on. Now, if we wait for a moment, our cluster, it takes a moment for our cluster to be created. Okay, our cluster is running, so we can choose client to connect. We will copy the password and discovery token. We'll copy this to the code you've just seen on the slide. So this is our discovery token, and our password will be this. Name of the cluster, test server, so everything is fine. So we can start our application. While it's starting, again, we have to wait for a moment, because after all, it's Java. But if we wait for a moment, we should see that it connects to our cluster, which is in the cloud. One more second. Yes, and it connected. We created a cluster only with one member because that is free, and yeah, it connected successfully to this cluster. So a short summary. What are the pros and cons of client server and cloud deployment? From the good sides, data is separated from the application. We also have separate management. So if we have like a peak load, then we just can scale up the cache server separately to our application. It's also programming language agnostic. So you can use any programming language you want because there is a well-defined protocol between client and the server. From the downsides, we need some separate ops effort, or we need to pay for the cloud solution. Definitely you have higher latency than embedded cache. And you need to think about your infrastructure configuration. And let me comment on this. So if you set up your on-premise cache server, then it's better if it's in the same local network than your applications to reduce the latency. Remember, like caching is, it has very strong requirements in terms of the latency, even stronger than databases, because we are in caching. Like Hazelcast is actually called in-memory data grid, so it's like we are in the domain of in-memory computing. That's why the requirements are very strict. Now, what to do if we will use a cloud solution? We still need to think about how to set it up. So first thing, it should be definitely the same region where your application is, because we don't want our calls from Poland to go to US, because that would be, the latency would suffer. But it's not only this. So the second thing, you've probably seen on the demo that we've selected the underlying cloud provider, which means that if your application is running on GCP, then you should select the underlying cloud provider as GCP, again, to reduce the latency. And that's the last thing. We provide something like VPC peering. So you peer your VPC with VPC we created for you, and then they are like in the same virtual network. So there is even no one router hop in between the communication. That's how we reduce latency in the cloud solution. That's about cloud. So you might think like, okay, like client server, it's and embedded things these are quite old things. So there's nothing new in what I've just said. So just a short introduction about Kubernetes. So Kubernetes, like if you never used it, no problem. This introduction is for you. So in Kubernetes, a deployment unit is called a pod, and a pod contains one or more containers. All containers in one pod are guaranteed to be deployed on the same physical machine. Now, usually in most cases, you will see that one pod contains just one container, which is your application container, and that's all. But sometimes you may add an additional container with some additional logic, like, for example, logging agent that will send your logs somewhere. And this additional container is called a sidecar container. And with this introduction, we can see how it looks like. So on this diagram, what do we have? A request goes to the Kubernetes service, which is a load balancer in a Kubernetes world. It load balances the traffic to the pods, to one of the pod. And then this pod, its application container, which receives the request. And then this application connects to the cache container, which is a separate application, but always running on the same physical machine. So it can always connect using localhost. So, and this all cache containers that form one consistent cache cluster. So when I see like this solution is kind of in between embedded and client server. It is similar to embedded because it's the same physical machine. We run on the same physical machine. We use the same resource pool from the machine. It scales up and down together with your application. And there is no discovery needed. It's always localhost. However, it's always also similar. It's also similar to client server because your application can be written in different programming language. After all, it uses client cache client to connect to the cache server. And there is some isolation between app and cache, which the sum, it may be good enough or not good enough. It's on the level of containers. This is how the configuration would look like again in Spring. So as you see, we set up static configuration to connect always to the local host. However, in the result, the whole system is not static, it's dynamic because we just know that the cache part is on the local host. This is how it would look like Kubernetes configuration. So we have our deployment with 2 containers. This application will be your business logic, so it will change. And this Hazelcast is Hazelcast server, so it will always be the same. Pros and cons of sidecar caching. So first thing, the configuration is again simple. It's programming language agnostic. We again have low latency, and there is some isolation of data and the applications. From the downsides, it's limited to container-based environments, which is probably not a problem because that's the direction all the industry is going. The management is not flexible again, so you have to scale up your cache together with your application. And the data is, after all, collocated in the same application pod. The last pattern for today will be reverse proxy. And reverse proxy caching will be something completely different. Because so far, always application knew about caching. So application was aware that something like caching exists. This time we will do it differently. We will put cache in front of the application. So this is our scenario, our diagram. Again, a request goes to our system. It goes to the load balancer. And now just before or just after load balancer, there's a caching layer. And so it's checked if it's in the cache. And if the value is found in the cache, it does not even go to the application. Obviously, it's based on the, nowadays you do based on the protocol level. So usually you may read it as it's based on the HTTP protocol level. A very good solution for this kind of caching is Nginx. So you use Nginx for a lot of things. It also has a feature for caching. So if you would like to enable caching in Nginx, all you have to do is to add this line. Obviously, there is more to configure, but that is like the minimum you can configure. There are some problems with Nginx solution. It's only for HTTP, which is probably not such a big deal, but it's not distributed and not highly available. That is a big deal. And the data is stored on a disk, which is not, data is not really stored in the disk, but it can be offloaded to the disk, which is good and bad. I mean, you probably see good sides of that. Like, good is that if we have too many data in the cache, then it goes to the disk. But from the downsides, it's like you are not guaranteed that your data is stored in memory, which is actually the case, for example, in Hazelcast, but you are guaranteed that the access to data is super fast because it's always in memory. You can use Nginx with some plugin like Redis or Hazelcast, but they are not very mature. Actually, for Hazelcast, it does not exist yet, but for Redis, there is a plugin which is actually not super mature. But you can play with this, and you can also you can contribute to this. It's open source. Now, I really like the idea of reverse proxy because we don't have to think about, don't have to change our application to introduce caching. So now we can even go one step higher and like to see like the last variant of the caching pattern, which is combining sidecar and reverse proxy. So we'll use reverse proxy, but at the application level. Again, our diagram is Kubernetes specific, and the flow is as follows. Request goes to Kubernetes service. It load balances the traffic to Kubernetes pods, but this time in the pod is not the application container that receives the request, but it is the reverse proxy cache container. And now this reverse proxy cache container checks if, at the protocol level, if such request is already cached. If yes, return the cached value. If not, go to the application container, which performs some business logic, get the response, cache it, and return back to the requester. Now, all this idea that application does not even know that it's being cached, it has some good side and bad sides. Let's be optimistic and start from why would you use this kind of caching? So let's start from the good points. This is our diagram from beginning of the presentation. So a classic microservice system. We have a lot of services, they use each other, they are written in different programming languages, they have version, it's complex. Now, if we use reverse proxy sidecar caching, we could say, I don't want to change the code of any of these applications, but I would like to introduce cache here and here, and that's all. So at the declarative manner, at the configuration level, you specify which services should be cached. And that has a lot of power because you no longer, you will not break anything, or it's just super convenient and super nice approach. So this is how it will look like in a Kubernetes configuration. So let's start this time describing this from the bottom. So we have two containers and one init container. So let's explain first the containers. So starting from the bottom, this is our application, so it will change from, this is our business logic. Then caching proxy is this caching proxy part, which will be the interceptor of our requests. And then we also need an init networking container, which would change the IP tables in that way that that request goes not to the application as it would normally do, but goes to the caching proxy. Like this, normally any request on port 80 would go to the application container because that is the container that exposes the 80 port. But we make this init networking tweak to change the all requests on port 80 from outside goes first to the reverse proxy cache container. That is all the code for this init networking actually script. So we just changed the IP tables. Now, if we look on this diagram again, you may think it's similar. If you are really in the Kubernetes world, you may say it's similar to the Istio framework, and you would be right, because like Istio is that's the idea of Istio, that it uses the sidecar, which is more generic, to redirect the traffic. and to use for the security. And Istio actually plans to introduce caching. So when the Istio introduces caching, then this reverse proxy sidecar caching would be a really, really big thing. And they are close to implementing this because we are speaking with them, in contact with them, and they are close to. Even though you may see this GitHub issues from 2017, so may not look promising, but they are actively working and finishing this. But I also told you that this idea of application not knowing about cache, it also has some bad sides. So from the bad sides, like the biggest problem actually is in general in caching, not only here. Like in general, the problem of the caching is the most difficult thing in caching is actually cache invalidation. In other words, when to decide that the cached value is already stale, that it's already outdated. I should not use cache, but go directly to the database or directly execute some logic or to some service. And that is very difficult. And when you stick to when the application does not know about cache, it's even more difficult, because if applications are aware of caching, you can use some business logic to say, okay, remove me this cache. You can have some annotation in Spring. So application can decide when the cache is evicted. However, when application is not aware of caching, all it's left is just simple HTTP things like tags, like timeouts, basically timeouts. Yeah, when to decide where the value is not valid anymore. So that is like the biggest problem of reverse proxy caching. Short summary. So what are the good things about reverse proxy approach? So good thing is that it's configuration based. That is why you would use it. You don't change your application code to introduce caching. It's also programming language agnostic. It's everything agnostic. You don't even change application code, so no problem with that. And this approach is very consistent with containers and microservice world. And I actually strongly believe that will be the way to go soon. As soon as Istio implements it, as soon as it becomes stable, that will be the way we code in near future. From the downsides, we already mentioned like the difficult to invalidate the cache. There are no major solutions yet. For reverse proxy itself, you can use Nginx with the issues I mentioned. For the reverse proxy sidecar, until it's implemented by Istio, there are no like really good solutions. We implemented a prototype, but it's more on the prototype level than something that you could use in production. And it's also protocol based, which is probably not such a big deal. So with this, we came to almost the end of this presentation. As a quick summary, I will not repeat anything I've said before, because that could be boring for you. So as a quick summary, what I propose is very simple, oversimplified decision tree, how to decide which cache pattern is for you. So the first question I would ask if I design an application is, does my application needs to be aware of the caching? If no, do I run containers? If no, use reverse proxy. If yes, use reverse proxy sidecar as soon as there is a major solution for that. Now, if my application needs to be aware of the caching, the next question is, do I have a lot of data or do I have some security restrictions? If no, do I need to be language agnostic or do I run containers? If no, run simple embedded distributed cache. If yes, use sidecar solution. Now, if I have a lot of data or some security restriction, then the last question to ask is, if I run in the cloud, if no, use client server. If yes, use cloud solution. So this is, as I said, it's a little oversimplified, but it's a good starting point to how to find yourself in this caching topologies. Now, as the last slide, a few resources I recommend. So the first one is our blog post on how to use Hazelcast as a sidecar container. Second one is this reverse proxy sidecar caching prototype, again from Hazelcast. Third one is the caching best practices. It's not really related to this talk, but it's a very good blog post about about general caching and the practices, good practices. And the last link here, it's a very good video talk about Nginx reverse proxy caching and how to use it. So I really recommend watching this. And with this last slide, I would like to thank you for listening to me. And let me now check this Slido, if I managed to open this, if there are any questions, because we still have four minutes. If there are any questions, I will answer them right now. Okay, there's one question from Alex. Thanks for asking the question. I'm really happy that I don't see that I see at least one question. So question is, from your experience, how many solutions use single caching mechanism versus utilizing caches at multiple levels? What are good best practices? So this is like a very good question. But unfortunately, there is no good answer to that, because I would like a good answer is should we use like multiple level caching or like single level caching is I would say it depends, but it depends is never a good answer. So in general, I would strive for there's like a very good rule of thumb that you should cache only at one level, because like when you cache on multiple levels, then it's very difficult to debug your system, because you are really it's very easy to get lost. You know, I got this value from somewhere, but where it was really cached. This obviously is like so this is a very good rule if you don't have to just cache on one level, but sometimes obviously you need to cache on multiple levels because you would like to so because like you would like let's say have one cache against your whole system, and against each service has its own cache. So the thing is, like, I would say never cache in more than one places, like for each service. So each service should have only one cache. However, you may have multiple levels, like one is at the service level and the second one is at the system level, or like a bigger component level. That would be the I don't know, Alex, if I answered your question, but the question is generally like it will super depend on your architecture and on your system. Since there are there are no more questions, I thank you again for listening, and goodbye.